Hello everyone, today let's take a look at QP141, another order stats question. So we basically have x1 and x2 as IID random variables with uniform distribution between 0 and 1. So we let y be the minimum of them and we let z be the maximum. So in part A, given that z is less than or equal to some fixed value of z, what is the probability that y is greater than or equal to some fixed value of y? So x1 and x2 are both coming from a uniform distribution. Y is distributed as the minimum of them and z is distributed as the maximum of them. And we're basically just trying to find the probability that y is greater than or equal to some fixed value of y, given that z is less than or equal to some fixed value of z. So basically what we're saying here, if this is my number line between 0 and 1, and we fix some value of z, and we also fix some value of y between them, and we're given that the maximum of these two comes before this fixed value of z, so that basically means that both of them come before this fixed value of z, because obviously if the maximum comes before the fixed value of z, then so will the minimum. So given that information, it's asking us what is the probability that our minimum between those two comes after this fixed value of y. So in this case, our minimum of them is going to be x1, and in this case, it does come after y, right? But if x1 came before y like this, well then our condition would not be satisfied, obviously. So what is the probability that they're basically in between this range right here? Well, it shouldn't be too hard to calculate. I'll just graph it out to make it simpler. We have x1 on my x-axis and x2 on my y-axis. They're both uniformly distributed between 0 and 1, so they fall somewhere within this range right here, right? Somewhere within this box. And we're given when we fix the maximum to be less than or equal to some value of z, so we know that the maximum of x1 and x2 is less than or equal to z. That basically just implies that both of them are less than or equal to z. So x1 is less than or equal to z, and x2 is less than or equal to z. So this right here is what the maximum implies. If we translate that to our graph, we have some fixed value of z. We know that x1 is going to be less than or equal to that value, so somewhere in this region. And we also have to have x2 be less than or equal to that same value. So if we have z up here, the same value that we did over here, we also have to be less than it. So it's just going to be this region right here, right? All of this. So now given that information, if we want to find the probability that the minimum of them, so y, right? The minimum of x1 and x2 is greater than or equal to some fixed value of y. Well, that's just basically the same thing as saying that both of them are greater than or equal to that fixed value. So x1 is greater than or equal to y, and so is x2. So if I have this fixed value of y right here, the region where x1 is greater than or equal to that is just going to be all of this. And I have the same fixed y for my x2. The region where x2 is greater than or equal to that value is everything up here, obviously. And also definition of conditional probability, the probability that y is greater than or equal to y, given that z is less than or equal to z, well, that's just going to be equal to the probability that z is less than or equal to z on the bottom here. And on the top, we have the probability that y is greater than or equal to y intersection z is less than or equal to z. So on top here, the probability that our minimum is greater than or equal to y and our maximum is less than or equal to z is basically when all of these conditions right here are going to be true. So the intersection between all of them, and that's just going to basically be this region up here that I'm going to shade green here. Then obviously the probability that our maximum is less than or equal to our fixed value in general is just going to be all of this region right here, right? It's just going to be these conditions over here. Because we have a uniform, just like we've done a million times, we can just think about probability in terms of area, right? This is our total probability space right here, 100%, 1 by 1 box. And then the probability that z is less than or equal to z is just going to be this blue area right here. So that is going to take up an area of just z squared. That's just because obviously we're multiplying a square with side length z. And then the probability of intersection right here, this one up here, is just going to be the area of this region. So that is just going to be a square with side length z minus y. So the area of that region is just going to be z minus y squared. So our final conditional probability right here is just going to be z minus y squared divided by z squared. This is also obviously under the assumption that y was less than or equal to z. That's just because if we have y greater than z, then the probability that our minimum is greater than or equal to that y value would just be like this shaded region up here, and the probability that our maximum would be less than or equal to z would be this shaded region down here. And obviously there's no overlap, that could never happen, so this is just not possible. So it's going to be 0 basically if y is greater than z. So this right here is the final answer for part A. So again, when you have a uniform distribution, because every single point in this joint distribution is equally likely, you can think about probabilities in terms of areas, which makes it a lot simpler to solve. Okay, so now for part B, which is certainly going to be the harder part, what is the correlation of y and z? So we want to find the correlation between y and z, where again, y is the minimum between x1 and x2, or x1 and x2 are uniform 0 to 1, and z is the maximum of these two, right? So the correlation. So we talked about correlation a good amount at this point. We know it's just going to be equal to the covariance between, what do we have, y and z, divided by basically the standard deviation of y times the standard deviation of basically z. We've also shown that the covariance is just equal to the expected value of x times y minus the expected value of x times the expected value of y. And we also know the standard deviation of y. We know that's just going to be the square root of basically the variance of y. And we know the standard deviation of z is just going to be the square root of the variance of z. So now we're just working with all the moments of the minimum and the maximum, which we talked about how they were distributed back in QP 139, right? So just like in QP 139, right, the density function of the minimum of two random variables, that's just going to be equal to 2 times basically the PDF of one of these variables, so f sub x of x, and then times the probability that the other one is basically greater than that. So that's basically just going to be 1 minus the CDF of x. So again, we can illustrate this with a number line. Basically what I'm saying here, if I have my number line from 0 to 1, so I'm saying if x1 is my minimum, which happens with this density right here, what's the probability that x2 is greater than it? So x2 being over here, and that is this right here. And then we're saying if x2 instead were my minimum, then what's the probability that x1 would be greater? That you get the exact same values right here. So that's why we multiply by 2, right? So now in our case, we're dealing with uniform 0 to 1s, right? So the density of x1 being at a random point, or x2, or any x that's between 0 and 1 is just going to basically be 1. That's the density of a uniform 0 to 1, right? Now, if we have the density for one of our points, let's say x, the probability that the other one is going to be greater is just going to be equal to basically, well, we have a uniform 0 to 1, so it's just going to be 1 minus x, the distance between here. So this is just going to be 1 minus x. So that is our density for the minimum, 2 times 1 minus x. And now let's look at our density for the maximum. And again, for the same reasons, which we also showed in QP number 139, basically the density of the maximum is just going to be the density of a specific point. So let's say we fix x to be some specific point. We're saying what's the probability now that the other one comes before that? So that's just going to be the CDF. We also have two different choices for our maximum, right? That's why we multiply that by 2 right here. So the density of a uniform 0 to 1 is just going to be 1 again. And basically the CDF, the probability that we're less than some value of x, is just going to be x minus 0, so x. So this density right here is just going to be 2x. So I shouldn't say equals here. I'll just do a little colon action. I'll say this is basically the density of y. So I'll say f sub y of y. And this right here is the density of x, so f sub z of z. We also further showed in QP 139, it was a long question, that basically the expected value of the minimum between two uniformly distributed between 0 and 1 random variables was just going to be equal to 1 on n plus 1, or in our case, n is going to be 2, so 1/3. And the expected value of z, the expected value of the maximum of two uniformly distributed between 0 and 1 random variables, was going to be n on n plus 1, where n is 2, so 2/3. So that takes care of these in our equation. Now this is going to probably be the hardest part. What's the expected value of x times y? So let's figure that out down here. Oops, I don't know why I keep doing this, but I keep saying x and y, but I should be saying z and y, right? The expected value of z times y, this should be the expected value of z, and this should be the expected value of z times y as well. Whoops, I keep doing that. But actually, to get the expected value of z times y, well, we have our joint distribution down here where we have x1 and x2. Z is distributed as the maximum between them, and y is distributed as the minimum between them. So the easiest way to solve this is just by realizing that at any given point in our joint distribution, we're going to have one of them be the maximum and one of them be the minimum. That actually makes it really simple to solve, right? Anywhere above this line, we're going to have x2 be our maximum and x1 be our minimum. And any point below this line, we're going to have x1 be our maximum and x2 be our minimum. But still, at any point in this joint distribution, one will be the max and one will be the min. So the expected value of the max times the min is basically, we're just going to sum up over every single possible combination of x1 and x2 and just multiply them together, because we're guaranteed, again, one of them will be the min and one of them will be the max. So the expected value of the minimum times the maximum, we can just write that as the expected value of x1 times x2, right? And then because x1 and x2 are completely independent of each other, right, we've already proven back in the discrete section of the roadmap, right, that when we have the expected value of two random variables that are independent, you can just express that as the expected value of x1 times basically the expected value of x2. Also, in previous parts, we know what the expected value of a uniform 0 to 1 is, right? It's just going to be 1/2. And same for this one, it's also a uniform 0 to 1. So 1/2 times 1/2 equals 1/4. So that's the easy way to solve that. But also, if you wanted to do it the hard way, let's just do that real quick. So if you wanted to calculate this straight up, right, we could just sum up over every single possible value that our maximum could take. So we're having z go from basically 0 to 1. And for every single one of those maximum values, we're going to have a minimum that will be less than that maximum, right? So then we can also take a double integral over basically 0 to z. Because obviously the minimum has to be less than the maximum. So if the maximum is right here, well, then we need a minimum between this point z and 0, right? And then we're calculating the expected value of z times y. So we have z times y within our integral times basically the joint density function of zy. Then we were doing the minimum in the first integral, so dy and then dz. So now we just have to figure out this joint density function between the minimum and the maximum, which we were already kind of doing in part 1, right? Or part A. So let's look at that. So if I have this number line over here, the density of z comma y, that's essentially like saying the probability that z is equal to little z and y is equal to little y. So we know that x1 and x2 are somewhere within this joint, or within this number line. So the probability that the maximum is equal to some specific value of z and the minimum is equal to some specific value of y, that's essentially what the density is. It's just going to be basically the density as if x1 were the greater value and x2 was the minimum, right? So the probability of x1 taking that specific value of z and x2 taking that specific value of y is essentially the density, right? Their densities are 1 each, so 1 times 1. And then plus the probability that instead x2 was equal to the specific value of z and x1 was equal to that specific value of y. In that case, we also have densities 1 times 1, right? So this is just equal to 2. Or you could derive that from the CDF, so big F of z comma y, that's just going to be the probability that both z is less than or equal to some value of z and y is less than or equal to some value of y. Well, the probability that our maximum is less than or equal to some value of z, again, just like we did in part A, it's going to be all of this region right here. Now, instead of the probability that the minimum is less than or equal to this value of y that we fixed, so let's say we fix this value y right here, now we're saying that the minimum is less than or equal to this value of y. So that's kind of like the opposite that we were doing in part A. In part A, we were saying the minimum greater than or equal to that value of y. We found it was all of this region up here. So now we're just saying the probability, we're flipping this, right? We're saying the probability that y is less than or equal to this value of y. So that's just going to be everything not in that box, right? It's going to be all of this area. And all of that orange area is just going to be the green area, right? Z squared minus basically this area right here. So it's just going to be z squared minus, well, what did we find in part A? We found that the area up here was just going to be z minus y squared, right? Because we have square of side length z minus y. This is just equal to z squared. When we expand this, we get basically, we're going to have a negative z squared. We're going to have a negative y squared, and we're going to have a positive 2zy, and then these are going to cancel right here. So we're just going to have 2zy minus y squared. And then we have the CDF of the joint distribution. So to find the PDF, we're just going to take the partial derivative with respect to both variables. So with respect to z and y, when we do that over here, this is going to be 0. And then this right here, both the y and the z will get differentiated out. So this will just be 2 again, right? So a bunch of different ways to find this. But essentially, once we found that, we can get back to actually solving this integral right here. So we need to solve the integral from 0 to 1, 0 to z of zy times 2, basically. So I'll just say 2zy with respect to y first, and then z. So for the inner integral, right, well, the outer one's going to be from 0 to 1, and now I'm evaluating this right here. 2z is a constant relative to what we're evaluating towards, and then we basically just have y squared on 2 as the antiderivative of y, obviously, and then we're evaluating that from z to 0 of dc. Now the 2's are going to cancel here, so we're just going to have this, and then when we plug in z for y, we just get z squared here, and we're going to have z times z squared, and then when I plugged in 0, I would have got 0, so minus 0, and then we just have basically the integral from 0 to 1 of z cubed dz. And now this right here is just equal to, well, the antiderivative of z cubed is z to the power of 4 divided by 4. Evaluated from 1 to 0, that's just going to be 1/4. So again, you can see we get the same exact answer that we did up here. The final answer for the expected value of z times y is 1/4. Okay, so now new page, I've calculated all these things that I can plug into the top, so I just need to basically calculate the bottom part. So first of all, the variance of y, we know what that's going to be defined as. It's just the expected value of y squared minus the expected value of y all squared, like so. We already know the expected value of y, so let's just calculate the expected value of y squared, the second moment of basically the minimum, right? So the expected value of y squared. So to solve that, all we have to do, well, I keep realizing that we mess up these variables up here all the time, right? This should be a y instead of an x, and that should be a z instead of whatever it was before. There's so many different variables that you have to keep track of. But basically, the expected value of y squared shouldn't be too hard. Well, we know that basically the density function of y is just going to be this one, this one up here. So we're just going to integrate from basically 0 to 1. The minimum can take values between 0 and 1 of 2 times 1 minus y, our density function, times y squared dy. So that's going to be equal to the integral from 0 to 1 of 2y squared minus y, actually 2y cubed dy. So the integral of this term right here is just going to be equal to 2/3 times y cubed evaluated from 1 to 0. So that's just going to be 2/3. And then for this term right here, we're going to subtract off the integral of 2y cubed, which is just going to be 2 times y to the power of 4 on 4 evaluated from 1 to 0. So that's just going to be 2/4, also known as 1/2. So that's just going to be equal to 1/6. So we have 1/6 here, and then we need to subtract off the expected value of y squared, which we found was equal to 1/3. So minus 1/3 squared, that's going to give us 1/18 here. Now finally, the variance of z, the variance of the maximum, we can calculate that in much the exact same way. It's just going to be equal to the expected value of z squared minus the expected value of z all squared. We've already calculated the expected value of z squared, so let's just find the second moment of z here. Again, I'm just going to integrate over all possible values that our maximum could take. So from 0 to 1, and what was our density? It was equal to 2z, right? So 2z times z squared dz, that's equal to the integral from 0 to 1 of 2z cubed. When I integrate that, I just get 2 on 4 times z to the power of 4. Plug in 1, I get basically 2/4, so that's going to be 1/2. So we have 1/2 here. This is going to be equal to 1/2, and then minus the expected value of z all squared, which was going to be 2/3. So minus 2/3 squared is going to be 4/9. And when I subtract 4/9 from 1/2, I get 1/18. So the variance for both will be 1/18. So now I have everything I need to find the correlation. Let's just plug in all the values that we just calculated, right? The expected value of y times z is 1/4. The expected value of z times the expected value of y is 1/3 times 2/3. So that's just going to be basically 2/9. So let me write that here, 2/9. That's going to be divided by the square root of 1/18 times the square root of 1/18. So when we multiply those, we're just going to get 1/18. Now on the top, let's get a common denominator. I multiply the left side by 9, I get 9 on 36. I multiply the right side by 4, I get 8 on 36. So when I subtract those, I get 1 on 36 on the top, and then I have a 1 on 18 on the bottom. So when I work that out, I'm going to get 18 on 36, which is just equal to 1/2. So that's the correlation between the minimum of the maximum, the correlation between y and z. So that is the final answer right here. So we have a positive correlation here, which makes sense because as the minimum gets larger, so should the maximum, and vice versa, right? So yeah, that was very complicated just to get an answer of 1/2 right there, but it's good order statistic question.